Morning, bom dia. So where we stopped? What we do? We study small oscillations. Of a Lagrangian system with n degrees of freedom. N degrees of freedom means that our vector has n components. So the generalized component has generalized vector has n components, and the system is given by the Lagrangian, which is what? Which is the sum of 1/2 of mass coefficients, velocities, so the quadratic form with respect to velocities, minus potential energy. So this system is conservative, so it conserves energy. So usually people refer to this system as a conservative from point of view that energy is conserved. So that if you change minus to plus, this is constant of motion. So this does not change along the any solution. But what we do, we want to solve the equation of Euler-Lagrange. So we consider Euler-Lagrange equations. Which are n equations of the second order. And what we do, we cannot solve them in original form, but we consider first we consider equilibrium solution, and then we consider near equilibrium solution. So equilibrium is a solution which does not change in time. No? That comes from what we indicated as equilibrium. So the system does not move. So all coordinates remain constant. In this case, obviously, derivatives are 0, first and second. And then what you can do, if you substitute this form of the solution into the equation of motion, the only thing which will be left is the derivative of the potential energy with respect to all components is 0. So that's a definition. That's a condition for the equilibrium, is that the equilibrium is a point q0, right? So q equal q0. So the condition of equilibrium is that the equilibrium is a critical point of the potential energy. And if you remember, the derivative of the potential energy are what we call forces. So it just means that all forces are 0. So that's a very natural condition. So when all forces are 0, then nothing. Then we can that point at which all forces are 0 is equilibrium. But in a variational form, it's a condition that all derivative, the gradient of the potential energy is 0. So what we do next? So we consider a motion near the equilibrium. So it means that we consider the vector dq, which is just how much we departed from the equilibrium. And then you can also consider its derivative. But derivatives are just the same as derivative of the original vector, of course, right? Because differentiating constant gives 0. And we consider them all small. We consider them all small. And if you consider them all small, that you can expand the Euler Lagrange equation, expand it in Taylor series. Around the point. So you see the left-hand side is a function, right? It's a function of what? Around a function of coordinate. Let's write it. Taylor series with respect to all arguments that enter here. So what enters here is coordinates, velocities, and also there is acceleration. So these are all variables that enter in this equation. So you can expand in Taylor series around the equilibrium. So Q0, 0, 0. So essentially you expand it in these variables, in this delta. The zero order term cancels. Zero order terms is exactly this condition that is exactly this condition. So the then there are linear terms, then in the Taylor expansion, then the quadratic terms, then the cubic terms, and so on. So what we do, we keep the largest order terms, which are linear terms. This is what we do, neglecting, which means that in other words, you neglect second and higher order terms. Which gives you equation of motion, which we derived last time. So it will be m delta q double dot plus c delta q equals 0. So what is what? So m is matrix, coefficients computed at the equilibrium. So it's n by n matrix. And C is also n by n matrix. With Cij are defined as second derivatives of. So the first derivative has 0, but second are not necessarily 0. So we take second derivative and compute them at equilibrium. So if you expand in a Taylor series, forget about smaller terms, the second, third order terms, keep on the linear terms. You get this equation which depend on mass coefficients at point Q0 and the second derivative at the equilibrium of the potential function. So that's, in other words, this is equation for small oscillations. Equation for small oscillations. So it's only valid as long as delta q derivatives and velocities and accelerations are 0. Velocities do not even appear, as you can see. It's only we have coordinates and accelerations. Okay, so that's how to solve this equation. So we need to solve it. So, okay. How to solve? So what we do, first, let's that's fine. First, let us just for simplicity. So for simplicity, we take equilibrium at 0. Then I just don't want to keep delta all the time. But you think that you remember that whenever we work with small oscillations, Q almost always means deviation from equilibrium. I just say that let's put origin at equilibrium, then I just don't need to keep delta every time. So we have to solve these equations. Very important properties is of this equation is a form of the matrices. So what are the properties of matrices? So the first property is symmetry. So remember, mass coefficients, they're symmetrical with respect to change of indices. And the stiffness coefficients, which are Cij, we call them stiffness coefficients, they're also symmetric because the order of derivatives can be, the second derivative commute, well, any order derivatives does not depend on the order how you take the derivatives. So that means that symmetry. First is a symmetry. So, which means that mass matrix is the same when you transpose it. Transpose, remember, is exactly changing the two indices. So this is operation which gives new matrix. But in our case, the matrix is the same. So if you change indices, which is in matrix form called transposition, T, it's the same matrix. But then there is another property which is correspond to the mass matrix. If you recall, so this is property 1. The property 2, we have to recall the origin of the mass matrix. So you see the mass matrix comes from the potential energy. So let's compute kinetic energy. So let's compute kinetic energy at the equilibrium. So that's what it is. On one hand side, it is this sum. So on one hand side, it is this 1/2. But on the other hand, from the beginning, we told that Q are just generalized coordinates which uniquely define position of the system, right? So, but the original system was written, can be represented as a collection of material points. So there is another expression for this. Kinetic energy is if we take all material points which constitute our system and just sum up their kinetic energies, right? So that's equivalent formulations. So now what we can see is that from this expression it follows that T is 0 if and only if. So this is if and only if. I will be using sometimes this mathematical formula abbreviation. So it calls if and only if. You see that we just remove the middle, it become abbreviated. So if and only if all velocities are 0, right? No. Otherwise, t is positive. And all velocity 0 is equivalent to say that all velocities in generalized coordinates is 0. So the same, we see that t is equals 0 if q dot equals 0 and t bigger than 0 otherwise. But now this t can be written as, you see, so this expression, this is mass matrix. So this expression can be written as q dot t m q dot t. So what we, at the end, we can say that we can write a definition so that we define m as a positive definite matrix is. So we say that M is a positive definite matrix, and usually in short we will write M bigger than 0. So if this quadratic form is bigger than 0 for any vector which is not 0. So that's a definition. That's a typical definition from linear algebra of the positive definiteness of the symmetric matrix. So if a matrix is symmetric, you can say more, that it's positive definite or not. So positive definite means that quadratic form that it constitutes is always positive except for the trivial situation when just it's 0, when the vector is 0. Okay, so that's it. So what we say, and we know from this property is that, since T is exactly the quadratic form divided by 2, so we know that matrix, so that's our second property, that mass matrix is positive definite. So we have symmetry and positive definiteness. Good. Okay, so then, let's try to find a solution. So first we focus on particular solution. So you say some solutions. So how we find solutions of this equation? So this is what we want to solve. So again, we use that property that we had before. So first property, so the important property of the system is that the system is linear, and it also with real coefficients. Or real matrices. So matrix M and C is real, and it's linear with respect to Q. So in principle, you can try to find not only real solutions but complex solutions. So we can consider complex valued solution, complex valued solutions. Values will be complex in complex Cn space instead of Rn. And then what you can say is that if Q of t is a solution, then taking real, so if Q is a complex solution, so then the left hand side can have real part and complex part. So, and both real part is 0 and complex part is 0. But real part is satisfied by real part of Q, complex part is by complex part of Q. So here it's important that matrices are real. So check, you can make this computation directly if you don't see it from the picture. But what you see is that real part and complex part, imaginary part, are real solutions, real valued solutions. So this is a very typical trick. So you in linear system, it's more convenient to work with complex variables, and you don't care because whenever you have complex solution, your real part is also solution, imaginary part is solution. And then the other is so this has to do with real coefficients. Another part is that if you have two solutions, say A and QB, well, let's say, okay, A and B are solutions, then any linear combination is also solution. CA, QA, CB, QB is a solution for any CA, CB, for any coefficients. So you can take any linear combination is a solution. So, so good. So we look for a solution in a specific form. Precisely, we take the solution as an exponent of some coefficient multiplied time by the vector. So everything is complex here. All coefficients are complex. So lambda we take complex, and u is a complex vector. So just we have right to do so. And now you substitute this formula to the equation, and try to select lambda and u in such a way that it becomes a solution. Okay. Yeah. Okay. So what happens? Every derivative takes lambda out of the exponent, right? So what you get m lambda squared. I put outside, and also I want to put outside the exponent m u. Oh, okay. Let's make it. So m by the second derivative. Second derivative will give you lambda squared e lambda tu, right? Then plus c e lambda tu equals 0. Well, exponent is non-zero, so we can cancel it. And the rest I will write as lambda squared m plus c u equals 0. So this is a n by n matrix. Right? So it's n by n matrix multiplied by vector u equals 0. So from linear algebra, we know that in this situation there are at least one, you have to have at least one of the two situations, that either u is 0 or the matrix has zero determinant. Well, both. So but we are not interested in 0 u, because if u is 0, then we just get trivial solution. Because trivial solution we're not interested. So that we know that if u is non-zero, it implies that the determinant of the matrix is 0. So that's our setting. And I can give some names so that in this case, so lambda is called, we call it eigenvalue. U is, we call eigenvector. And we call this equation as a characteristic equation. So the whole equation, this will be eigenvalue problem. And this will be called characteristic equation. We give name to every piece of it because this is what we get regularly in all other problems as well, in different forms, but with the same meaning. Okay, so then characteristic equation. So what is characteristic equation? Characteristic equation, determinant of the n by n matrix, if you remember the definition, is the sum of certain products of n components. So every component depends on lambda squared at most. So what you have is that this left-hand side is a polynomial of degree n, because you have n product of n components of this matrix with respect to lambda squared. So it's a polynomial with respect to lambda squared of like can be some coefficients a0 lambda 2n plus a1 lambda 2 n minus 1 until n to 0. So it will be a polynomial or with respect to lambda squared, right? So only even powers starting with the power to n. And from algebra, you know that it means that there are n roots counting multiplicity. So in principle, roots are not, there are n roots lambda squared. So lambda 1 squared, lambda 2 squared, lambda n squared. The polynomial of degree n has n roots, which are in principle can be complex. And some of them can repeat. So the idea about repeating the roots is because you can take this polynomial and represent it as a product of n monomials. Each one gives a root. So that's algebra. That's, I think, you should all know. Okay. So we have n roots. For each root, we can try to find u, and we have in principle many solutions. So let's see what we can do with these solutions. First thing that we will show, and that's not a general property, it's just property of this system. So let's prove a proposition that all roots lambda square are real. We started with we said from the beginning that they're complex. Well, if lambda square are real, it does not still mean that lambda is complex, right? Because if lambda squared is negative, lambda is imaginary. But we show that the squares of lambda are real. So let's prove them. How you prove? So in principle, so let us assume that lambda square, which is complex, and U, which is complex, satisfy R eigenvalue and eigenvector. So let's assume that they satisfy all these conditions. So now what we want to do, what we will do is that we will use, remember, I will recall what means Hermitian transpose. Hermitian transpose is a form of the transpose. We use T, right, many times, so which is just usual transpose when you flip coefficients. So Hermitian transpose is, we call it with a star. This is more physicist notations. Well, there are different notations. Sometimes you put star, sometimes you put H. Well, there are different ways. But we will use star. So image transpose, what it is. When you take complex vector, and it's the same as taking usual transpose and complex conjugation. So sometimes it's called just complex transpose. No, conjugate transpose, no conjugate transpose. So you take complex conjugation and transpose, conjugate. So it's like transpose, but you also take complex conjugation. So let us, so first let us show that U star Cu. So what is U star Cu? So this is a column vector. This is matrix, right? And this is transpose, so it will be row and complex conjugated. So it's 1 by n by n by 1. Okay, so the product will give you 1 by 1. Yeah? So just complex number. Okay, so let's show that this is always real. In general, product of three complex objects can be complex, but when you write it in this way, for any symmetric matrix, any real symmetric matrix, this product is real. So how you show it? We know that vector U is in principle complex. So let's separate the real imaginary parts. So V, W are now real vectors, which are real and imaginary parts, and just compute this expression. So what it is? It will be U star Cu. U star is a complex transpose, right? So applying to V, it's just transpose. Applying to IW, it's minus transpose. Then it comes C, and then V plus IW. Okay, open the product. So first it becomes VTCV. Then we take WI by minus I gives 1. So it's plus WTCW. So this is the real part. And then we take imaginary part. Imaginary part comes from this I. So it's VTCW. And minus WTCV. Okay. So we need to show that the real part, the imaginary part is 0. Okay. So now let's take this expression. And this is vector, matrix vector. So altogether, this is number, which is a real number. So what we can do, we can kind of transpose real number. Transposing real number make no change because it's just 1 by 1 matrix. But when you transpose, you can think of the real number as a product of vectors matrices. So you can put T inside this parentheses. So when you put T on a product, so you have to transpose each of them and put it in opposite sequence. So it will be V T, C T, and T of T is, so T is twice transpose gives you back the same vector. And now C is symmetric. So you see that this should cancel the other terms. Right? So what we have this well-known condition from linear algebra that whenever you take symmetric matrix and in general it's actually for any Hermitian matrix, just that we're not go into the details. So if you multiply by U and you Hermitian transpose, you get a real number. Not only a real number, but we know which real number. So this is this. Okay, so real. We proved. No, we didn't prove. So we just proved that it's real. Okay, the same you can do with M. So same way, similarly, you can show that this thing is also can be written as in that form. But now it's not only real, but it's also positive. M. Because M is positive definite. So it's always positive if U is non-zero. So it's both real because both of them are real, but we know more that it's positive. So it's essentially what's important is non-zero. So that's almost it. So now you take this equation. So since it's lambda is eigenvalue, U is eigenvector, you take this equation. Know that it's satisfied. Since it's satisfied, we can multiply on the left by the Hermitian transpose, open the parentheses, so we get U star mu lambda squared plus U star cu equals 0, and you find lambda squared. You can divide by this. This is positive, so it's non-zero. So you can find lambda is minus U star cu divided by U star mu, and this is real. Yeah, so we find that all eigenvalues are real. And since eigenvalue is real, then this expression is real. And okay, so we proved what we want. That's it. So the simple observation that since lambda squared is real, we always can take the eigenvector also real. Yeah, because eigenvector is a solution of this equation. Taking eigenvalue, we guarantee that there is a solution, but we can always take it real. If you take a complex, the real part is also a solution. So we can always choose eigenvector to be real. So now we have this solution. We kind of found the way how to find solution of this form, and let's just see what are these solutions. What is the property of these solutions that we found? Okay. So there are three cases. The lambda square is real, so it can be positive, negative, or 0. So let's start with negative. So this is first option. So the lambda square is a negative. So then lambda is the square root of the negative value, so it's plus minus I omega. Right? So here we say that omega is square root of minus lambda square. And in this case, the solution that we found is U is real, you know, but this is not. So this is E. And let's take with a plus. Whenever you take plus and minus, we get to the same result. So at the end. So we take this, and then remember what is exponent. It's cosine t. Omega t u plus I sine omega t u. And we know that both real part is a solution and imaginary part is a solution. So we have two solutions at hand. And we also know that linear combination is a solution. So we get a solution in the form A cosine omega t plus B sine omega t u for any coefficients, real coefficients. So we found actually many solutions. And this is, of course, oscillatory solution. So this is exactly the solution. So if you take, okay, so this is the periodic oscillations. This is periodic oscillation with frequency omega. So that's periodic function. So second option is lambda squared positive. So in that case, taking the square root, you get lambda equal plus minus sigma. I'm trying to keep the same notation as with before. So here sigma is square root of lambda squared, the positive version. And then, so here we don't need any more taking real imaginary part because everything is real. But we have two options. So we already have two solutions, one with plus and another with minus. And we can take a linear combination, it's still a solution. So let's take a linear combination. So this is a solution. So this is for, again, for any A and B. Okay, and so what happens is that sigma is positive, so this solution has the following form. So the second term at large times becomes 0, and this could be increasing unlimited. So this is unstable. Unstable solution. So what happens with solution? So the first term will become large. And at certain moment, even if you start it near the equilibrium, it will go far away. So when it goes far from equilibrium, already the equation that we consider is not anymore valid. So what happens with the solution? So at certain moment, the validity it goes far from the equilibrium, and we cannot use anymore this equation. So the solution is not anymore valid. While here you have periodic oscillation, so the solution is approximately valid all the time. Okay, and then the third condition, the third case is when lambda squared is 0. So what you can show, so when lambda is 0, somehow this is 1, so you just have a solution which is u. So, and it's constant, so you can think that this is, somehow you get just one solution of this form with any coefficient by u. But what you can check is that if you add any coefficient multiplied by time, so this is a solution for any. So again, we have two coefficients, so let's see y. So let's see y, and this is y. Why is it so? Because our equations have this form. And you just substitute it in. And you see the second derivative will kill both terms. And what will be left is c by the coefficient which you can take outside because it's just number. Cu equals 0. And this is 0 because lambda squared is 0. Because if lambda squared is 0, that Cu is 0 just from the eigenvalue problem. So actually, even when lambda squared is 0, even though you directly just get one solution, but you can also guess a second. Okay, so we have many solutions. So the next step is to construct the general solution. Let's construct all solutions. Slow. So in order to construct all solutions, you take a theorem from linear algebra that I'm not going to prove. But anyway, from linear algebra, we know that if in the case when M is a symmetric matrix, positive definite, and C is a symmetric matrix, there are n roots. Not necessarily different. So that's our roots of the polynomial. So they can be repeated, so they can be equal. Some of them can be equal. But what is important is that with n linearly independent eigenvectors. And we already know that everything can be real. So this is also real. This will prove that they're real. So what this theorem tells is that you can we know that we can associate to each eigenvalue eigenvector. But what they tell that these eigenvectors, sometimes this is not unique. So this is not unique way how you can choose eigenvectors, especially if two lambdas, if lambda 1 and lambda 2 are the same, then there is no unique way maybe to choose eigenvectors. So theorem tells that you can choose eigenvectors, yeah, so satisfying our eigenvalue problem. Such that you get eigenvector for each eigenvalue, and then all linearly independent. So this is actually the essence of the theorem. Linearly independent. You can always choose n eigenvectors, but the theorem guarantees that they're linearly independent. So what this means, I'm not going to prove this theorem, but it means that U1, Un is a basis in a space. So that's essentially the property we're going to use. So now, to each lambda, we have two solutions. And we can construct a general solution. So we can construct a solution as a sum over all these eigenvalues. And depending on the eigenvalue, or if it's positive, 0, or negative, we take either the first one, so it would take the first one, ai cosine so this is if lambda squared is negative. If it's positive, we take that solution. And if it's 0, we take that solution. So we take n vectors. So for each we can have a solution, and we can take some of them with different coefficients. So the second property that we can prove is that this is actually a general solution. That Qt with arbitrary coefficients. So we have n coefficients A, n coefficients B. Is a general solution. So general solution means that it solves the system equation of motion that Q double dot plus CQ for any given initial condition. And remember, initial condition means that you give 0 position and 0 speed. So given initial condition and 0 speed, you can choose coefficients that solve it. So let's show it, and then we'll have a break. So proof. Well, essentially what we have to show is that we can choose coefficients A and B. So that gives, we already know for all A and B, this is a solution. So all we need to show is that we can choose A and B such that it satisfies the initial condition. So what we do is just compute what is Q0. So Q at 0 is what? So you put 0. So here cosine will be 1, sine will be 0. Exponents, each of the exponents is 1. And this is 0. So we get a sum. It will be AI UI when lambda I squared is negative, right? Here we get AI plus BI UI, and lambda I is positive, and AI UI I squared is 0. And we just call it sum of the alpha I UI. So alpha I is just prefactors. It's A if lambda squared negative, it's AI plus BI is lambda I is positive, and AI is 0. So for each eigenvector, so each eigenvalue, we define coefficients, and what you see is that this equation is just expansion. This is just expansion in the basis. Expansion in the basis. in Rn, which means that there exist unique coefficients alpha which solve this condition. So alphas we define uniquely by the first initial condition. So now we have to do with the second initial condition, for the velocity. So we have to compute velocity. First, let's compute velocity in general. So it's a sum over all modes. And then you have to differentiate this expression with respect to t. So what it gives, so from cosine gives minus ai omega I sine omega I t. It will be plus bi omega I cosine omega I t ui. So this is one squared negative, right? Then differentiating exponent, it will give you minus plus ai by sigma, and another will also by sigma. So it's, we can just, oh, no. Like this, plus, minus. Right? And the last, differentiating the last, it will be bi ui. Good. So now we take it at initial point. So this is 0. This gives 1, right? So it will be bi omega I ui. Here you get exponent gives 1, so it's ai minus bi sigma I. And here it's just the same. Okay. So let's just call these coefficients beta. So what is beta? It's bi omega I, ai minus bi sigma I, and bi. Okay. Again, this is an expansion in the basis. Which means that whatever initial condition you give, there are unique betas which satisfy this condition. Okay, so we have unique beta, unique alpha. And what remains is to find A and B, AI and BI. And this is not so hard because look what we have. So AI, so whenever lambda I is negative, we just take alpha I. Or when it's positive, you can combine this with that. So what you can do, you take alpha I divided by 2 plus beta I divided by 2 sigma I. It gives you I exactly. And then it's just alpha. Okay, and beta, and B you find in a similar way. So you find B from here. So it's beta I divided by omega I. Then from this and that, you express B as alpha I over 2 minus beta I over 2 sigma I. And then from here you get the last. So that's it. So what we did, we showed that you can satisfy both initial conditions by choosing the right coefficients A and B. Not only right coefficients, but uniquely given coefficients. So that shows you that this is really a general form of the initial condition, because that for every A coefficients it's a solution, and any initial condition give unique values of these coefficients that give you general solution. So that's it. So let's make break till 1, 2. Okay. So let's continue. So I'm going to show example. Example. So let's consider some sequence of springs and masses. So the oscillatory system. Between two walls with two masses, so there's a mass M, and springs which also have the same coefficients, stiffness coefficients. So it's kind of we already considered just one spring, so it's linear oscillator. Now we have two, then you have three more. On if you have many of them, this becomes a model for the one-dimensional crystal. Right? So these are atoms with elastic interactions. And then with this model, we can go to wave equation, if you like. So this is kind of the first step to make it harder. So two masses, and they are identical. There are identical springs, and we have two walls. So how you describe this system? So first, coordinates. So everything moves in horizontal direction. So we take the coordinate. The two coordinates they have to describe position of the two masses. So the first coordinate we call x1, and we compute it from the position of equilibrium. And also we can compute the x2 as a position of the second mass. So the x1, x2 is the position of each mass computed starting from the equilibrium. So we have equilibrium position. So any displacement gives you x1 is given by this x1, x2 coordinates. So from this you can immediately write the kinetic energy. So it's m x1 dot squared, mass velocity squared by 2 for the first mass and for the second mass. And then you can also write potential energy. Potential energy is the energy of each of the springs. Right? So the interaction of mass with the wall, between the masses, mass with this right wall. So we already wrote that mass of the energy of the spring is a coefficient by the deformation of the springs. This is Hooke's law. So in that case, it's x1 squared by 2. And all the springs are the same, so we have to do the same here. The deformation of the springs squared is x2 minus x1 squared. And the last spring is 2 squared. So then, and from these two, you construct Lagrangian as a difference. Good. So the next step is that we write equation of motion. So this is Lagrangian equation. There will be two equations. With this Lagrangian, t minus u. So the first term we always, when kinetic energy has this form, we know that it is always this mass by acceleration. So the first equations will be mass by acceleration for the first and mass acceleration for the second. The second term will be, it will come with plus because it's minus here, minus here. It will come with a plus. So we have to differentiate u with respect to x1. So these terms gives you k x1. And from here, when you differentiate square, you get k by x2 minus x1. But then x1, it comes with minus, so it will be minus. Equal 0. And then now you differentiate this with respect to x2, so it's this term gives you x2 minus x1, and this term will give you plus k x2. So this is equation of motion. So now you can just simplify this a little bit. It will become k1 plus, so it will be 2 k x1 plus k x2. Zero. The good part about these equations is that they're already linear, right? We already considered them. So equilibrium is already q equals 0. So q is our vector x1, x2 is 0. And they're already linearized. They're already linear. So there is no need to linearize. So that we can write these equations as mq double dot plus cq equals 0, right? So this is, so now you can find what are the metrics. The matrix M is M0, 0, M. And matrix C, which gives these coefficients, is 2k minus k minus k to k. So you see, as promised, they're both symmetric. And this is obviously positive definite whenever M is positive. And mass is positive. So M is symmetric, positive definite, C is symmetric. You see, so because if you flip indices, it doesn't change. Okay, so now the first step is to find eigenvalues. And we know that eigenvalues are determined from the, it's not here. So from the fact that determinant of this equation should be 0. Determinant of this matrix should be 0. The determinant of the lambda square M plus C should be 0. So what this matrix is, so that let's just write them. So it will be lambda squared M plus 2k minus k lambda squared M plus k. Determinant of the 2 by 2 matrix is product of diagonal elements minus product of anti-diagonal. So this lambda squared M plus 2k, there is the same number, so it's squared minus k squared. And this we can write as difference of squares, so we can factorize it. Lambda squared M first from with a minus, so it will become plus k, and another with plus. Right, no? And if it's 0, so either this 0 or that 0. This gives you 2 eigenvalues. So first eigenvalue comes from the first product to be 0. It will be minus k over M. And the second is minus 3k over M. Again, as promised, we get 2 eigenvalues such that squares are real. And both negative. Both negative. So both negative. Good. So then the second step is eigenvectors. So how to find eigenvectors? We have to write equation. We have to solve now equation which is lambda squared M plus C, U equals 0, and we have to find U. So taking the first, which is minus Km, K over M. So what the matrix becomes? The matrix, so you subtract K from here, so it will become K minus K. minus kk. So you substitute this into here. M cancels. It will be 2k minus k, so it will be k. Same k here, minus k there. So it gives you eigenvector as 1, 1. 1, 1 is satisfied. And the second, minus 3k over m. 3k, when you put minus 3 plus 2, it gives you minus 1, and minus k. And this gives you second vector, which will be 1 minus 1. Again, as promised, linearly independent. So they give a basis in the space. And finally, we can use the general formula of the solution. And we only have the negative eigenvalues, negative squared of the eigenvalues. So we can write a general solution as so it will be Q of t, which is x1, x2. So it becomes first term, it will be a1 cosine omega 1 t plus b1 sine omega 1 t by the eigenvector. Produce a2 cosine omega 2t, b2 sine 2t by the eigenvector. And remember that we have two frequencies. Omega 1 is square root of this. And omega 2 is square root of the second. Good. So finally, we can interpret what did we get. So physical interpretation. So mathematically, we found all solutions. So whatever initial condition you give to the system, so whatever initial position you put, initial speed you put, we know that we can choose these four coefficients, a1, a2, b1, b2, such that this is a solution. So now what this solution means, and in fact, this solution has two pieces. There is mode 1, with mode 1, which is a periodic solution with a low frequency. So there are two frequencies. One is smaller, another is larger. So this we call lower frequency because frequency is smaller. And this is solution mode 2, also periodic solution with high frequency. Already the sum is not anymore periodic because you see they have a rational relation because one is square root of 3 times the other. So together they are not periodic, but there is a periodic motion plus periodic motion, and then you get a superposition of the two, the sum. So let's just consider separately one solution and separately the other solution. So the mode 1 is what? So mode 1 is when the mode 1 is when the first and the second mass move together because first coordinate and the second coordinate are exactly the same. So if first mass is moved on have some displacement, the second mass will have exactly the same displacement. Like this. So two masses move. So essentially, it's motion like a rigid body, keeping the same distance between each other. So two masses move together, and since it's kind of moving motion of the rigid of the body with twice bigger mass, this is why it is slower. So the frequency is smaller. So mode 2 is the opposite situation. Mode 2, whenever one mass goes left, the other mass goes right, or the same amount, and vice versa. So they move in opposite directions. So you see, whenever one mass moves, for example, first mass moves right, the second mass should move left. Like this. So this is a motion against each other. And this is kind of, well, your intuition should tell you that this is stiffer type of motion, so the frequency should be higher. So this is low frequency, and this is high frequency. And the general solution is this sum of the two. So if you start with this initial condition, you will just see this mode. If you start with this initial condition, you will just see the second mode. But if you start with arbitrary initial conditions, this will be sum of the two modes. Okay, and okay, so that's our solution. So now I can give you an exercise. It will be for the Monday, not next week, but next week. Just for those who did already the second exercise. So exercise. It will be list 3. This is 4. Let's fix a date. '30th of January. So the three exercises. So first, let's consider the potential. Well, it will be looking like a sugar loaf, powder sugar. So we take some level. So there are 3 levels. So there's one level, another level, another level. So this is potential. So what I want is so draw a phase diagram. So remember we did. So draw a phase diagram for the system with this potential, without dissipation. So just original for the original Lagrangian problem. Second problem will be just the one that we considered, but now we'll make it harder. We put 3 masses. So 3 identical masses with 4 identical springs. It's the same problem, but one more mass. Of course, you have to put coordinates x1, x2, x3. So we have now three coordinates. So what you have to do is just everything. So write Lagrangian function. Write Euler-Lagrange equations. Find eigenvalues and eigenvectors. And general solution. And free interpretation. Of all modes. So you will have three modes, of course. So if you have two modes, you will have three modes. So this is second, and the third didn't enter. I put it here. The third is proof that if the two eigenvalues are different. No, let's see. Let's make it complete formulation. So for the eigenvalue problem, C with our matrices. So, proof that if you have two different eigenvalues, then their eigenvectors are orthogonal with the matrix mass in the middle. This is orthogonality condition. Orthogonality of modes. You see it here, right? Our remember, our matrix M was just M1, 0, 0, 1. And you see clearly that they are orthogonal. Eigenvalues are different, so vectors are orthogonal. So you just can show that it's always the truth. For any different eigenvalues, eigenvectors are guaranteed orthogonal. So that's so in that form, all modes of the oscillations in the Lagrangian system are orthogonal in this sense. So when you measure, if you define a scalar product with the mass matrix. Good. We have time. So we'll move to the next topic. So the next topic is oscillations in non-conservative systems. So what means non-conservative? So all these previous systems, we call them conservative because they conserve energy, but actually principally it's the property that they are Lagrangian. They're given by Euler-Lagrange equations for certain Lagrangian. So now we will consider the extended version as we defined below. Before, so the equation, we consider the system which are given by equations where left-hand side is a Lagrangian equation. And then there can be external force. So it's a case where the vector q just does not describe the full system, full isolated system, but just part of the system. And then the equation of mode for part of the system has external force, which in principle depends on the rest. So there is a large class of models, which we will consider in details in different physical situations. So the usually, in order to know this force, you need to know how the rest of the system moves. But this is certainly not useful. So whenever you write equations, whenever you define vector q, which is a part of the whole of the full universe, you find it you derive in such a way that you have some model for this force. And model means that you define this force somehow in terms of the coordinates of the original system. So we'll consider a class of models where this external force can be expressed as function of coordinates and velocities. So that's not all models. Sometimes you just have function of coordinates, sometimes coordinates velocity. In principle, you can even have higher derivatives. Sometimes some model require that you know the history, not only depend on q, but on the q before in time. So there are plenty of large kind of models. So we will consider these models, which is already a very large class, and I say these are the models that most frequently used. Okay, so now this is an extension. So now, as we have this external force, we don't anymore conserve energy in general. So we will call them non-conservative systems. And again, I want to solve it. I want to solve it with assuming that this force is given. Whenever it's given, we have equation of motion. So how to solve? We cannot to solve them in general, even though we don't understand so far all the properties of their motion. As I mentioned, mainly because of the chaotic behavior, because chaotic behavior is not completely understood yet. Much is known, but not all. So again, we consider equilibrium. So let's consider oscillations. So oscillations around some state that we know, equilibrium. So equilibrium is a solution which is constant. Again, we know that derivative of the constant is 0. Second derivative is 0. And then we know that whenever you substitute this into the left-hand side, everything disappears except for du dqi. So before it was 0, so we knew that derivative should be 0. But now the right-hand side is not 0. This is a condition. Or you can remember that we can define internal force just as derivatives of du dq1 with a minus. Remember that the force is, we were defining this force. Qn, right? So this is minus internal force. This is plus external. So you put them all in the same side. And you naturally get this condition that f internal plus f external equals 0. So that's condition that there is equilibrium when all forces cancel each other. The internal force cancel external force at certain position. That means that the system can stay in this position forever. So what we want to do is we want to we now consider small oscillations near the equilibrium. So small oscillation near the equilibrium means that delta Q, which is distance to the equilibrium in configuration space, and also velocity, and so on. So all of them are small. And since they're small, we can use, again, the Taylor expansion. So we already did Taylor expansion for this part. So now we need Taylor expansion for external force. We'll take Taylor expansion. We'll take external force. And Taylor expanded around at the equilibrium, at position and zero velocity. So it gives you the value plus what I will write, then I'll explain what it is. So then it's actually Jacobian matrix. I'll just in a second say what it is. Again, at the same point, delta Q plus delta Q dot and higher order terms. Second order terms and so on. So what is written here, you see that this SF is vector, and it has n variables. So whenever you take derivatives, this is a matrix. So F. So what we say dF external dQ is actually n by n matrix. So you take the first component and differentiate with the first variable. Then you take first component, differentiate with the second variable, and so on. On the second line, you take second component, differentiate again with the first variable, second component, differentiate with the second variable, and so on. So it gives you n by n matrix called the Jacobian matrix or Jacobian matrix. So whenever you have vector depending on a vector, derivatives of all components with respect to all arguments gives you matrix. So this is a matrix, and this is also a matrix. So this is n by n, and this is n by n. Okay, so now we're very good. We just put this expansion. So we can expand this in Taylor series, expand this in Taylor series. So we expand both sides in Taylor series. So we expand for the equation for the equation of motion. So we take d dt dl dqi dot minus dl dqi external q dot. So for zero order terms, it is already satisfied, because for zero order terms you exactly get this equation. Then next is linear order terms. So there are linear order terms, there are quadratic terms, cubic terms, and in principle all terms should cancel each other. So now we keep only linear terms, neglecting much smaller quadratic and higher order terms. So just linear terms you keep, and this gives you what we call linearized, the system linearized. This gives you the system linearized near the equilibrium. So what linearized comes from the fact that we just keep linear terms. We already know what is this. We did it before. It's m delta q double dot plus c delta q. And we know what will be on the right-hand side. On the right-hand side, we will have these two matrices. These are two linear terms. So we just keep them. Okay, and now I put everything to the same side, and I'm getting the general equation. And I call this L. Let's call it K. Q equals 0. This is our equation. Where what I did, so I define L as minus this, right? Minus and I called K as C minus the other Jacobian. That's it. So we have an equation of motion linearized. It has this form. You see, it now has not only second derivative but first derivative. And in principle, matrices L and K arbitrary. We don't have any more symmetry condition on them, but we have symmetry condition on M. M is still positive, definite symmetric, but L and K, we don't know what it is. So what we are going to do next is that we will classify different type of forces that appear in different models, which define essentially symmetric, antisymmetric parts of these two matrices, and see how this equation can be solved and what it gives. And before that, we will give some more, and together with the solution of this system, we give some a more solid mathematical description of all the procedure, because so far the connection between these two systems is somewhat not very rigorous, because what we did, we took the system which we consider to be an exact original model, and then we neglected some part of it, and said that now we consider the simpler version, because we neglected second order terms, third order terms, and so on, and we have this system. So it's good to have a more precise understanding of what is a connection, right? So that we guarantee that what we find is correct. For example, why we need is, for example, we say that, for example, imagine that you find that this system has a solution which is stable, does not go far from equilibrium, which is in principle does not guarantee that the same happens here, because these terms that we neglected, okay, they're small, but they're small, which means that if we stay near the equilibrium, the difference between the solutions is not big, but at some finite times. But if you consider it long times, there's even small change, if it can accumulate with the time, just can give instability. You see, so that even if you neglect something small, but you consider it at large time, the effect, the small multiplied by large, can be large. So that's why it's actually good to have exact relation between properties of this system and this system. So we will make clear rigorously what actually which conclusions from this equation which we can solve, we can actually guarantee that this is also true for the full model. Okay, so and there will be interesting examples for what happens. So now we don't conserve energy because of external force and all this kind of. So that's essentially the all realistic models that we consider in mechanics. So that we, with dissipative forces, with other kind of forces. So let's see what will be. So this is for Monday. Let's see.